So in Chapter 12, we're going to touch on two pretty major topics in chemistry, but we're going to actually be fairly brief on both of them. These are topics that in a normal two-semester general chemistry sequence, we'd probably spend double or triple the amount of time on these topics. So we're just going to get some of the basics, especially on reaction rates. But these are both very important topics for a number of reasons. And so we start out by talking about chemical kinetics. So first of all, what are chemical kinetics? Well, this is the study of how quickly chemical reactions occur. So just because it's favorable for a reaction to occur doesn't mean that the reaction actually will take place. And we saw an example of that previously when we discussed the idea of activation energy. Activation energy is the minimum amount of energy needed for a reaction to occur. Well, in addition to all of those things we talked about previously, none of those talk about how quickly a reaction occurs. And so we can talk about two different reactions here. Let's think of, iron, any source of iron rusting. And then let's think of vinegar, which is an acid, reacting with baking soda, which is a base. Now think about what you know about those two reactions. Do they happen at the same speed? And I think we all know that the answer for this is no. If we mix vinegar and baking soda together, we get a reaction almost instantly. As soon as you add them together, you're seeing the reaction of acetic acid and sodium bicarbonate to form sodium acetate plus water, and then the reason you see the bubbling, plus carbon dioxide. And that happens almost instantaneously. But if you have a piece of iron sitting out, it's going to rust and form iron oxide. We all know from experience that that reaction doesn't happen instantly. That reaction takes days, weeks, months, and maybe even years for it to take place. So if we consider a reaction of A going to B, we can talk about the rate of this reaction in two ways. Because the rate is going to be the change in concentration over the change in time. And so we could consider that as the disappearance of the starting material, disappearance of A. So that would be a change in the concentration of A over time. Now we put A here in brackets. The brackets here indicate that we're referring to the concentration of A. We could also talk about a reaction in terms of the appearance of one of the products. In this case, that would be compound B. So we could talk about the change in the concentration of B over time. And these two values should be related. How would they be related? Well, as A disappears over time, B is going to appear. The only difference is because A is disappearing, it's going to go down, B is going to increase. And so we would have that these should be of the same magnitude, but of opposite value. All right, now what are the things that can influence the rate of the reaction? And in this course, that's what I want to focus on. What are things that actually change how quickly a reaction occurs? So maybe stop for a minute and take a couple minutes and write down a couple of factors that you think could have an influence on the rate of a reaction. And then we'll talk about a whole bunch of them. So the one that might be the most obvious is concentration. And why do I say that might be the most obvious? Well, let's go back to our original page. And notice that I said the rate was the change in concentration over the change in time. So certainly changing the concentration is going to affect how quickly the concentration will change or be able to react. So for most reactions, increased concentration of reactants increases the rate of the reaction. Now, why is it that that's the case? Well, in order for a reaction to occur, what has to happen? So let's say we have two molecules of A here. And here they are far apart from each other. What has to happen in order for these to react? Well, they can't react when they're far away. They need to come together. They need to collide in order for them to be able to react. Only at that point, when they're in close enough proximity to each other, can something actually happen. Now, let's consider what happens when we raise the concentration of a solution. So here's two beakers. They're both going to have various solutes divided in them. And let's assume that each of these red dots is one of the reactant molecules. So over here is low concentration. Now let's look at one of higher concentration. At much higher concentration, what's more likely to happen? At that point, the molecules are much more likely to come in contact with each other, and it's much more likely for a reaction to occur. So in general, higher concentration equals higher rate of reaction. Second thing is temperature. So again, for most reactions, if we increase the temperature, that increases the energy. If we increase the energy of our molecules, then we do two things very quickly. So this is going to increase how quickly the molecules are moving. So anytime the two molecules do collide, they're going to collide at higher energy. And because they're moving faster, these collisions will happen more often. So as a result, we increase the temperature. This increases the energy of the reactants, of the solution. We get more frequent collisions. Those collisions that occur at higher energy, and that allows for the reaction to happen faster. All right, what about catalysts? So first thing, what is a catalyst? So a catalyst is a substance that increases the rate of reaction but is not consumed by the reaction. All right, and in a little while we'll talk more about how that works. Finally, our fourth item here is sort of a vague one, and that's the nature of the reactants. So we say that anything that allows for better collisions can increase the reaction rate. And this can include things like what state of matter everything's in. So a reaction will take place that's going to take place could be very different if you're dealing with solids versus liquids versus gases. Whether your compounds are dissolved in solution or just by themselves. For a solution, what solvent are you using? And many, many other factors. So again, just anything that leads to better collisions among the molecules. All right, but not all collisions actually lead to a reaction occurring. What will make that determination? Well, typically we're looking at the energy of the collision and the orientation. So we can have a very large molecule, but if the wrong part of it is what comes in contact with the other molecule, then they're not going to react. So for every reaction, there is a minimum amount of energy that we need. And without this minimum amount of energy, nothing will happen. Now you might be asking, aren't a lot of reactions what we call exothermic? Exothermic is a term that means the reaction gives off energy. But if you think about it this way, we've used this example many, many times in this class for many different things, so we'll use it again. So we know that octane, or more specifically isooctane, is able to be burned as fuel for our cars. Does this reaction happen spontaneously? Well, hopefully the answer is no. Because if this did happen spontaneously, then whenever you go out to your car, there won't be any gas left. There might not even be a car left. So what has to happen for this reaction to take place? We have to provide a certain activation for it. And so for any reaction, we can plot the energy of the reaction versus the reaction progress. And for an exothermic reaction like this one, a very general graph might look like this. Here's our starting material, here's our products, and here's the path that we use to get there. Now, this is not the path for the combustion of octane. That one would have a graph that is much, much more complicated. But notice, we can talk about a difference in energy between the starting materials and products. And notice in this case, the energy of the starting material is greater than the energy of the products. That means the reaction is giving off energy or is exothermic. And this is probably the best example, most straightforward example of an exothermic reaction is combustion. We can also have reactions that go the other direction. So starting materials at low energy, products at high energy. These are known as an endothermic reaction because they're taking reaction in, or taking energy in. What's an example of an endothermic reaction? Well, probably the most important example would be photosynthesis. Plants take in energy from the sun and store that energy within a molecule. But back to our exothermic reaction. So we do have that the energy of the starting materials is greater than the energy of the products. But before we did that, we actually went up in energy, as designated by this red line. And so this is known as the activation energy. The activation energy is the minimum amount of energy needed for a reaction to occur. So for any reaction, we always need to put in energy first, even if that reaction is going to give off energy at the end. Now, if you think about most combustion reactions, you don't keep having to put energy into them. You just do it once and the reaction keeps going. That's because that the reaction then gives, once it's started, it gives off enough energy to keep going. All right, so why does this matter? Well, if two molecules collide to try and react, if they don't have this minimum amount of energy needed for them to react, then nothing will happen. So let's look at this another way. So here we have molecule A is going to react with this other compound. This is going to be a single displacement reaction. And we're going to get a new bond formed and a new bond broken. So if we put this back on our graph, over here we have our two starting molecules, and over here we have our products. What's up here? So this is known as a transition state. And might have that new bond A to B partially formed, and that bond that's leaving B to C partially breaking. So the transition state is an extremely short-lived activated complex at the top of the activation energy. When we say short-lived, how short is short-lived? Now, these transition states only survive for about 10 to the minus 13 seconds. And that's because, if you think about this, this is the highest energy point on the graph. So it's energetically favorable for it to go back to starting materials as well as back to product. So typically these transition states don't last very long.